start. So I would like to invite Slovakia to present their solution, and starting now.
Okay. Hello, everyone. My name is Polonec, and for Team Slovakia, I would like to present you our solution to problem number 2, air muscle. So the problem statement is following. Place a balloon inside a cylindrical net, as is sometimes used to wrap garlic, and inflate it. The net will expand and shorten, and our task is to investigate the properties of such a muscle. So firstly, let's introduce our setup. It was completely airtight, and it allowed me to measure the pressure inside the balloon and the height of the mass. Uh, at first glance, it might look complicated. However, let's break it down part by part. So a simple air pump was used to pump a known amount of air inside the balloon. Just to be double sure, a one-way flap was installed to make the setup more precise and rigid. And the air inside can be freely distributed towards the U-tube and the muscle. The U-tube is filled with water and was used to measure the pressure inside the balloon. And on the right side, we have the muscle consisting of the balloon and the net with some weights hung below. So overall, these were all the parts of my setup which I used throughout all my measurements. And truly, in the demonstration, we can see that once we are inflating the balloon, the net expands horizontally, therefore needs to shorten vertically. The net in this phenomenon is very important because that's what actually transfers the force, and that's what makes this system work as a muscle able to lift some weights. So when talking about the properties we would like to investigate are the muscle shape, the lift height, the efficiency of such muscle, and the muscle pressure. So to obtain the muscle shape, we need to analyze the shape of the balloon and the shape of the net around the balloon. So we know that the balloon has spheroid-like shape, which depends on mass, and this relationship we have measured. Also, the mesh shape around a balloon can be divided into multiple zones. So they consist of 2 cones and then one region where the net is touching the balloon. So that was for the muscle shape. Now let's investigate the lift height. For that, we need to describe the geometry of the net and calculate its arrangement around the balloon, and for that we can get the lift height. So a simple analysis, when we pump a known amount of volume, we get to know the shape of the balloon. Once we know the shape of the balloon, we get to know the circumference at any given point. And since we know the circumference and number of nodes in the net, we get to know the distance between them. And since another geometrical property is the size of one eye of the net, the assumption that our net is unstretchable, we get to know the spacing between the different layers. For that, plus the number of vertical layers in the net, which is another of its properties, we get to know the whole mesh arrangement, which, as you remember, is accounted for into these 3 regions. And that is exactly what our simulation does. So the parameters that we input to it are the geometrical properties of the net, such as the net height, net width, and size of the grid. And the properties of the net, since it is made from a one piece, there is no friction between the braids or nodes, and it is also non-elastic. Another very good benefit of our simulation is that we can actually visualize the nodes and make a qualitative videos like this. However, when we see like the plot, it greatly predicts our measured values for the balloon lifting the mass. So that was the lift height predicted from our simulation. Now let's take a look at the efficiency. So we need to do some energy calculations, and we define efficiency of the muscle as the work it does divided by the energy inside it. The muscle energy can be obtained from the pressure to volume dependence, which was measured as an integral of this, and it depends on the mass hung below. And the work done by the muscle can be calculated from the lift height of the mass. Once we plot these energies, we see a constant efficiency as the slope of this curve, in this case at around 5%. However, once we do it for multiple masses, we can plot the efficiency like this, and we see that it should converge to some value. So let's break it down theoretically. We know basically that the efficiency can be calculated as can be seen from the equations, where the lifting work can be obtained from the geometrical simulation. And now let's look at the energy inside the muscle. So the energy inside the muscle is converted into the lifting of the masses, the work of it, the energy into stretching the rubber, as a balloon is made out of rubber, and some heat losses. We know the work, however, let's look further into the energy of rubber and energy of heat. So the energy of rubber can be obtained from measuring a balloon with no mass applied, and it turns out to be at around 10 joules for 4.2 liters. And we came up with a creative solution to how to basically estimate the heat losses. So we introduced a plastic bag, which its walls were not stretching, therefore no energy was lost to the rubber stretch. However, we were still inflating the net, so the losses were to the heat. So only inflating the net without any rubber stretch, and we can rewrite the equations with some effectivity of lifting. And this effectivity can be also measured from, we measured the pressure inside the plastic balloon, and this effectivity turned out to be at around 40%. So therefore, we know that the maximal lifting energy without any stretching of the rubber can be at 40%. And once we rewrite the equations for our muscle, which is the rubber muscle, and account for the rubber stretch and also the effectivity of lifting, we get to know the efficiency of our muscle. And it is quite great that our theory actually predicts our measurements, and it is, in my opinion, great match, and without fitting any parameters. So that was for the efficiency. However, now let's look into the muscle pressure, and we can derive it from the muscle energy. So since now we know the efficiency of our muscle, we can rewrite the inputs and the energy of lifting as values we know, since one of them is the work from our geometrical simulation, and one of them is predicted from theory, the efficiency. And after differentiating this equation, we get to obtain the pressure inside the muscle. And this is quite unbelievable to me, how greatly this curve predicts the pressure inside the muscle, and to remember without fitting any parameters. So that was the muscle pressure. However, in my opinion, we are aware of some theory limitations, of course. So the shape which was measured, the ellipticity of the balloon, does actually depend on the volume. It seems that after a certain volume, it gets constant. However, with smaller volumes, due to the manufacturing of the balloon, it is a source of error for our theory, because our theory assumes a constant ellipse ratio, and that basically clears out the discrepancies at the beginning of our lifting simulation, the geometrical one, and also a bit at the pressure. Also, we examined multiple relevant parameters of this muscle, such as the size of one grid. So we cut the net to quadruple the grid size. Our simulation predicts that this should have no effect, and it is really intuitive, since we can imagine the net as just holding the balloon inside, and it was confirmed with our experiment. Also, to change the net length, we sheared it, so it is shorter. Our simulation predicts this effect. It was also measured, and after comparison, I believe it greatly matches. To change the net width, we decided to zone down the net. Our simulation predicts that this should have the most impact, and it really did. After comparison, we obtain another great match with another relevant parameter. So to conclude, I believe we constructed a stable apparatus, predicted the muscle shape, and from that, geometrical simulation predicted our lift height. We were able to theoretically predict the efficiency of our muscle, the pressure inside it. We are aware of some limitations, however, we did multiple measurements. Thank you very much for your attention.
Okay. Okay, thank you for the excellent report from you. The first question would be, what is the accuracy of your YouTube pressure measurement?
I believe it is quite accurate, since the height of the...
Can you give me the
Yes, the height of the water was measured to the point of millimeters.
from the millimeter? That would be quite a few Pascal. Okay, so next, how do you ensure that your system is airtight? Because the balloon is known to be porous.
Yeah,
and
great
it could
question. So,
leak air
for
as time
example,
progresses.
like in this picture, we can see like all the tube or pipe connections were
No, but I mean the
coated with
leakage from
Teflon
the
tape.
balloon itself, not from
Sorry?
this joint. The leakage from the balloon itself, the balloon porous surface, not those.
I don't believe like the balloon should leak air from the surface.
And is the net relatively tight or loose during the pumping process?
Since there are weights hung below, it is tight.
So the net is naturally trying to restrict itself into its original shape, right? Is this correct?
No, the net follows the balloon's shape.
Okay, I will discuss
So
about
it
this later.
adapts to the balloon.
And is the shape of the balloon measured with net present?
Sorry?
With net being present?
Yes.
Okay. And is the PV curve being theoretically determined, or is your model semi-empirical?
No, it is theoretical determined.
Okay. And can you show your simulation on slide number 67?
Mm-hmm.
Okay, can you run the simulation?
The video, yeah?
Yeah, the video.
Mm-hmm. So it is the change
Okay.
of parameter net width, and that is what is happening at at the video. So the volume is kept constant, and we are changing the net width.
Okay. And do you have any justification to why your value of efficiency is defined that way?
Well, of course, since the energy inside the muscle. Okay, I believe we don't have time for this.
Okay, so I will be presenting my opposition on problem number 2, air muscle. The problem states that place a balloon inside of a cylindrical net, as some is sometimes used to wrap garlic, and inflate it. The net will expand and shorten. Investigate the properties of such a muscle. Okay, so the phenomenon explanation on the theoretical part, the reporter say that the inflation of balloon causes radial expansion, and since the balloon is contained by the net, there is an actual contraction of the balloon similar to what can be observed in a muscle. And the work done was calculated by utilizing the gravitational potential energy, the muscle efficiency, and the overall the efficiency of lifting, and also energy dissipation from heat and to the rubber. And it utilized the equation of energy of muscle equal to the work from lift, and also, they have included the limitation of the theory, which utilized an ellipsoid to calculate the geometry of the balloon as well as the cone to calculate the geometry of the net. The assumption can be shown here. Net geometry assume that there are two cone shapes and the balloon is an ellipsoid, not a sphere here. There's a mid-tech. And the experiment have utilized an air pump, a one-way flap, which is freely distributed throughout the U-tube filled with water. It utilized a plastic bag to prevent energy loss and used in the auxiliary experiment. The parameter being changed include the muscle shape, the lift height, the muscle efficiency, and pressure. Now next, for the reported evaluation, the task performance, I think it's fair. They have clearly investigated the main property of the air muscles as well as the relevant parameter, but they do lack some qualitative explanation on the effect of varying muscle property as been asked in the problem statement. For the experiment, it's good. They use one-way flap to prevent air loss from the system, and various experimental graphs were shown. However, the hysteresis analysis was not conducted. For the scientific explanation, I think it was good. There was some utilization of clear visual diagram, making it easy to follow for audience such as me to follow. And the qualitative explanation, although the qualitative explanation was kind of lacking because there were no explanation on how various parameters such as lift height affect the overall phenomenon. And the model used, I think I would unfortunately have to give a lacking because there were no quantitative explanation to how the balloon inflate, as well as the model being seemingly semi-empirical. I might discuss about this later on in our discussion. And various assumptions were made in the theory that lack sufficient evidence to validate the assumption, also leading to an inaccurate model to represent the phenomenon. So for the discussion point, I have 7 main discussion points. The first being the assumption of an ellipsoid balloon, and other assumption about the system geometry. For the next discussion point, I will discuss about the net cone modeling on why, even though there are constriction on the net being preferred to return to its original shape, there is still a modeling of a net cone instead of like other kind of curves such as a catenary arc or other stuff like that. And for elastic net with no friction and no slip, I would like you to elaborate on this assumption more. And also a seemingly semi-empirical model on how you measure the PV curve experimentally and use this to find eta, and then use this eta to return to calculate whatever parameter you present in your report. I think this is like a circular radical fold, and I think I should need some justification to why you do this. And then I would like to discuss the extreme case of a very high efficiency at a very high mass. I would like to see if the muscle can actually stall at a very high mass and could not contract. And also the hysteresis of the balloon, has this been controlled and is this been included in the theory, as well as the elaboration on the efficiency of the muscle overall. And I would like to kindly invite the reporter to the discussion. Okay. First off, on the assumption of the ellipsoidal balloon and the net cone modeling, so you model the cone as a net. Because the balloon, as you can see here, although it is cylindrically symmetric, so symmetric on all sides, but on the top and the bottom you can see the balloon have the mouth, the neck, and also its overall bulk, which is elliptical shape.
Yeah,
so
like if I may comment, of course we are aware of the limitation with lower volumes, as you can see from the picture, that truly this shape is quite complicated, and it is because of the complicated rubber processes and the way the balloon was manufactured. However, with large volumes, it is true that it has an ellipsoid shape which was measured, and and matched
okay.
well.
Okay, seeing from this graph, I think I get an idea now to why you're. Can you show slide number 28?
Mhm.
So as you can see here, the ellipse ratio is kind of off when the volume is low, and on the slide 78,
Yes.
there are some
Yes. So this.
there's some deviation during when the air volume is low. I think this is the exact explanation to
Yes.
why the value
Yes,
of the simulated
I
and
believe
measurement data is
I
deviating.
exactly said this point in my
Yeah.
presentation that the discrepancy in the ellipse ratio causes the
Okay.
error at the beginning.
Okay, thank you. And next, let's move on to your choice to model the net as a cone. So you say that the net remain tight during the pumping, and also the net tries to like come back to its original shape. I think this means that there is some tension within the net, and that
Yes.
the net try to like restrict itself, and this would form not a cone but a catenary arc or some a more complex shape. Do you think you can justify why you use the cone here?
Well, since this is purely geometrical, and I think it is really reasonable to assume, since you can see quite a good match
But no.
with this geometry, like even, and like from the picture, I believe like it is cone-like.
Okay, it might be cone like when the balloon is large, but I don't see the reason to why it
I
is very
believe
similar
like
when the balloon is
we have
small.
a video.
Can you show? Because I can see the curve here.
Here. Yeah, so I believe to assume a cone is valid for this problem, since the geometry
Okay.
matches our measurements.
Okay, if you insist, I would like to agree to disagree, because I think modeling, since you have already made the simulation, you could go one step further and model the net not as a cone, but as a catenary arc, to ensure that your theory is more sophisticated and match the theory better. And the next one, I would like to ask you about the assumption you made. Are there any assumptions that you have made that haven't been included in the report?
Well, probably like some assumptions around the net, that it is completely elastic and there is
Okay,
no
so
energy loss in
these
the
one you have
friction.
included in the report. So
These
can
were
you
included in
justify?
the report, yeah.
Okay, so I understand that the net is elastic, but
Non-elastic.
there's no friction in the node. But are there friction between the nodes and the balloon? And has this been taken into account?
Well, I believe very low, since we imagine the net as to firmly press into the balloon,
Okay,
so the net intersections don't move around the balloon.
Okay, that is the case when the balloon is already in contact with the net. When it remains in contact with the net, it will remain that way throughout the duration of the pump. I can observe this in your
Yes.
in your
However,
experiment. But
we
please listen to me first.
Okay.
But during the phase that these nodes come in contact with the balloon, you can see here there's some contact point being shifted around. You can see.
No. I believe like what we see on the video is that immediately after the balloon on the video, please. Immediately after the balloon touches the net, it holds it in place, and only like a further rubber expansion is happening below.
Oh, okay. Okay, if you insist.
So the points in the middle stay placed at the exact spot in the balloon.
Okay, if you insist that there is no slip during the experiment, I think your assumption is true. There is no work done by friction, and your model is correct on this part. And also, can you elaborate to why the value of efficiency or eta muscle and eta lifting is defined that way in your report?
So you can imagine the efficiency of lifting as just filling the net, however, with no losses to the rubber stretch, right? And so this value was used in the calculation of our overall muscle efficiency, which actually this curve converges to the efficiency of lifting by the plastic bag. So you can imagine that with very significant masses, the energy of a rubber stretch, which stays constant, will be proportionally very low. So here it plays a significant role since it is proportionally higher, but further into the masses, it gets
Oh, I
lower.
think you are saying the effect of mass on efficiency. I'm trying to ask you for justification for your definition of efficiency. Why is it the energy divided by work or what you have shown here?
Well, that is how usually efficiency is
I
like
think that's very similar to efficiency in thermodynamic system.
hmm?
Is it like that?
Like the energy efficiency is like the output we gain from the muscle, so how much it lifts our mass dependent on how much energy was like put inside it. So the energy
Oh, okay.
like
So the
inside
energy
it.
you put in is E muscle,
Yes.
right? Okay. I start to see why you use it now. And I would like to ask your seemingly semi-empirical model on the PV curve. Do you have like a theoretical explanation or theoretical predictability on the PV curve that is not based on the value of eta or based on any prior value that you have found using auxiliary experiment or prior experiment? Do we have like a solid rigid?
We firstly independently measured the energy which goes into the rubber stretch.
Oh
So
yeah, but this is measurement. This is not prediction.
yeah, it is independent measurement which was used in our theoretical model.
Okay,
And
although it is dependent, although it is independent from your main experiment, I think that you should have like theoretical prediction of what actually happens here. Because right now you just compare the E input and E lifting with a balloon being restrained by the cage and not. I think
what do you mean restrained by the?
being inside the net and not being
No,
inside. The net.
in also in the independent measurement, the net was present. So it is truly like independent measurement which was used in the theory, and I believe this is okay and like often used, and even like for such complicated thing like stretching a balloon, it is not, as you can see from the shape of the pressure curve, not so easy to predict
Okay,
based on
I would
all
like to
properties.
disagree here. Although I agree that it is difficult to be modeled, there's quite a different
Right.
model to be used to model this curve exactly. We have the Ogden hyperelasticity model to perfectly describe this curve,
Well-
as well as another approximation like the Rydbergs model.
Well, we were able to like come up with our like own approach, which at the end used only independent measurements
oh.
without any fitting of parameters,
Oh,
and
okay,
it greatly
you have not
matches.
quite convinced me yet, but let's move on to the next. On the extreme cases of very high mass, your efficiencies seem to shoot out, seem to increases without any limit. Do you think there is a possibility that the
with
efficiency?
limit. The limit is that the theoretical curve converges to the efficiency of the plastic bag. Like we
okay.
already, I believed like we already agreed on this, that this curve with very high masses converges to the efficiency of lifting by
No,
plastic bag.
Do you think this efficiency would infinitely increase depending
No,
on the mass?
it would
so the
converge.
muscle would eventually stall and couldn't lift the mass. Is it right? And can you your
well, I
theory
believe
can it
we
predict this?
would reach another experimental limitations since
Also,
after hanging,
you haven't predict the limitation of the lifting weight of your model, right?
we observed the experimental limitations since after hanging
Okay.
a
Let's
mass
move on
around.
to the final point, which is the hysteresis. Have you taken into account the hysteresis and have you observed the
I
hysteresis?
have prepared an appendix slide for this. So actually, yes, there is hysteresis present. We can reach states
And how do you
with
control the
deflation.
hysteresis?
However, in the problem statement, it is clearly stated that we should inflate the balloon, so we did not explore this further.
I think it should be taken into account by either by stressing the balloon multiple times before taking the main experiment. Okay.
We exactly did that.
Oh, okay, then you are correct. Okay, for the summary of the report, I think the discussion was very fruitful, and I agree and also disagree with many on various points with the reporter. The assumption of ellipsoidal balloon, I think he have made a very good justification on the range on when the balloon was very large, but for the balloon was small, I think we agree that the theory cannot explain it that well because, and I also agree that it's quite hard to predict and model. So I think we can agree to disagree here. And also on the net cone modeling, I think the shape of the net is very close to the cone, close enough that you can use the approximation. The elastic net, no friction, no slip condition, I think this is true. And the seemingly semi-empirical model, he couldn't convince me quite enough yet that his model have some predictability and does not rely or base upon a circular logical flow. And the hysteresis, I think, should be investigated, but he have elaborated that he has investigated the hysteresis.
Thank you for the very insightful discussion. Firstly, to the reporter, you say you used a plastic bag in some of your experiments. Could you elaborate on that?
Yes, so the plastic bag was as a creative solution to like get rid of the energy lost to the rubber stretch.
So do you replace the balloon with a plastic bag, or do you put the plastic bag around the muscle?
No, there was no balloon, only a plastic bag.
So
We can tell that this is like a fall balloons which are usually
so your plastic
manufactured.
bag is inside the muscle now.
No, there is just a plastic bag and a net is wrapped around it.
Okay, sure. To the opponent, do you believe that using this plastic bag is justified?
I think this is not justified at all. The plastic bag can undergo plastic deformation as well as the energy loss
Okay, thank
due
you.
to heat would still be present.
So to the reporter, again, you have a lot of graphs where you plot like length against the volume. How do you obtain the volume of your balloon?
The volume, since we know the volume of the pump, and therefore we can recalculate it by the number of pumps.
Wait,
And this was also verified from checking the shape of the balloon and actually in agreement with.
So do you track the volume of the balloon?
No.
But you tracked how many pumps you had and
Yes.
you turned that into volume. How do you do that?
Sorry?
Doesn't this give a pressure? How do you check? So you measure the number of pumps.
Yeah, we measured the number of pumps and then
Okay.
we checked on the YouTube the height of the water level, and from that
Yeah,
we
I see, I
recalculate
see.
the pressure.
So do you have comparisons for your theoretical shape to your experimental shape?
Not really, because like the shape was used in
I see.
in
To
the
the
simulation.
opponent, do you think there's a better way to measure the volume of the pressure in the balloon? To the opponent. To the opponent, do you think there's a better way to measure the volume or the pressure of the balloon?
There is, you could use a truncated cone approximation and you integrated the volume using
Right,
visual
thank you. Do you think, so you mentioned that there's friction between the nodes, right?
Yes.
Could you elaborate on that?
I do not mean between the nodes, but between the node and the surface of the balloon.
Oh, between
so
the node
if
and the
there's a
surface of-
slipping between the nodes and the surface of the balloon as the balloon is inflating, there will certainly be work
Okay,
done by
I
friction.
see, thank you. So to the reporter again, you
Yes.
believe that the friction between the node and the balloon is insignificant, right?
Yes, because from the way the net is manufactured, we can see that it is actually one piece
yeah.
of plastic,
Yeah, yeah.
so no braids go like
I see. Okay,
around
thank
each
you.
other or something like that. So
Yeah, thank you. Could we go to slide 46?
yes,
46, what equations do you solve to get this graph?
the previous one,
Oh, this okay.
one.
Then can we go to slide 67? What equations do you solve to get the shape of the balloon? Shape of the muscle?
The simulation. So there are just the ellipse
It's just the ellipse.
ellipse equations.
some length is lost. Yes. Okay. Good morning, everyone. I'm Austin from Singapore reviewing air muscle. So on to the report. So I believe the report had a few strengths, which was a good experimental setup, where they used a one-way flap to ensure that there was no backflow of air, and they used a U-tube to measure the pressure inside the balloon. I believe that it was also good that they had a qualitative video of the phenomenon for us to have better physical insight and allow us to picture this phenomenon better. I think there was a clear explanation of some trends, and there were no fitted parameters used, which greatly increases the predictive power of his theory. I think there was also a very good experimental scope as he varied his net length, the grid size, and the width of his net. However, I think that the reporter had a few areas of improvement. Firstly, I didn't think he fully answered the problem statement because he used a plastic bag instead of a balloon in multiple experiments to remove the dependency on the elastic restoring force of the rubber in the balloon. I believe that this does not fully answer the problem statement and detracts from a very important part of this phenomenon. I also think that the elliptical shape assumption is not always applicable, as a round balloon does not always contact the net initial stages of inflation. I also think that the strand length is not conserved due to the geometry of its net used, as the hinging in the joints between the nodes results in changes in the length as the angle changes. So that's also another limitation in his shape model. I also think he characterized the Back's PV relation experimentally when it was under no load, which does not apply to some of his experiments. And he also had an unclear and oversimplified theoretical model neglecting many things. For the opponent, I think it was good that he pointed out the inadequate quantitative model, especially for the shape. And he also pointed out that the qualitative explanation doesn't include the elasticity or the restoring force of the balloon. And he also discussed the validity of his shape assumptions. However, I think that the opponent missed clarifying whether a balloon or a plastic bag was used in his theory data verification. And also, he had displayed poor time management, provided a lack of suggestions, and missed quite a few points. So on to what happened in the discussion. So firstly, the reporter and the opponent discussed the limitations of the shape model. And I do agree with the opponent here that the conical net and ellipsoid shape the reporter assumes is only valid when the plastic bag or balloon is significantly inflated, which results in it completely touching the net. And we do observe deviations at low pressures in the reporter's experimental data as well. Next, they moved on to the discussion of friction. And the opponent raised the point that there would be friction between the nodes and the net and the balloon. And the reporter countered this by saying that there was no slipping occurring between the balloon and the net. And I do partially agree with the reporter here that the friction between between the net and the balloon is not significant, but I believe that the way the nodes are connected can result in them exerting some sort of restoring force that is not accounted for theoretically. Next, they discussed about the PV curve of the reporter. And the opponent said that the reporter's theory was too empirical, as he had to characterize the PV curve himself. And I agree with the opponent here, and I believe that the PV curve should have been solved for by accounting for the characteristics of the rubber. And I also think that the way the reporter characterized his PV curve was incorrect, and the way he measured the volume by counting the number of pumps is quite experimentally inaccurate. So about the final verdict about this report, I think the reporter did qualitatively explain how the phenomenon occurs due to the constraint of the mesh, and he modeled this phenomenon basically, but did not account for friction, properties of the rubber, geometry, or the dynamics of the system. And the opponent did rightly point out the oversimplified quantitative model and lack of qualitative assumption and consideration for elasticity. And I believe the reporter has not fully answered the problem statement, as they used a plastic bag instead of a balloon, and that detracts from a very important part of this phenomenon, which is that a balloon will be used inside the muscle. Thank you.
Yeah, so firstly, I would like to thank very much both the opponent and the reviewer for their feedback and the discussion. However, I have some concluding remarks. So unfortunately, it seemed from the review that the reviewer completely missed the point that all of the experiments were conducted with a balloon, and the plastic bag was just as a creative solution to measure the efficiency of lifting as another independent measurement. So balloon was used actually in all of the measurements. Also, I think my theoretical model is valid since we input the independent measured quantities inside it, and therefore we get to predict our experiments. Also, the assumptions of zero friction or the assumption of the constant strength length are valid since the net since how the net is constructed. Also, the pressure inside the balloon is approximately the atmospherical one, so there is not much of compression. So therefore, I believe the volume calculation was valid. So I believe like this was one of the concerns of the reviewer. So I believe the volume was calculated correctly, and also we accounted for the geometry. We measured the ellipse ratio of the balloon, which was used in our geometrical simulation, which again greatly matched our data. Overall, I believe like a lot of work was done in this presentation, which were maybe not noted with the opponent or reviewer. So I believe I enjoyed it presenting, and once again, thank you very much.
Okay, questions from the jury panel? Yeah.
To the reviewer, you asked how did the reporter measure the volume? And did you think that it was the efficient way to measure by pumping numbers?
No, I don't think it's very experimentally accurate because the pump is quite inconsistent over different runs. So I think simply measuring the number of pumps might not be able to fully account for the volume.
I'd like to ask the opponent, how was the net they used constructed? How was it constructed? Just tell me, how was their net, how was it constructed?
So you have nodes, and between nodes.
I'm looking at the picture. There.
Yeah. How is it
I mean,
constructed?
I know what a node is, and it's just a joining, but you're not telling me how it was constructed.
Well, it was constructed.
I see the pattern there. Yep. And
Yeah.
can you tell me any more about how it was constructed?
Well, it was.
Yes or no?
Yeah, I can tell you. Well, the net was constructed between a string which was connected to a
String?
node,
String.
and when these strings are pushed away from each other, they are buckling and bending during the joint because the joint want to force the string to be in a vertical direction.
Okay,
As
thank
you
you.
can see in the node. This
Fine.
is where the
Thank
restraining
you.
force came from.
Right.
To the reporter, when you cutted the net and made it double the size, can you once again explain, not the shredded one, when you cutted the middle ones, can you explain, you got same result for efficiency or same result for what and why?
Yeah, so this is just the geometrical simulation. So what it predicts is the lift height, so how much the mass is lifted. And yeah, so you can see it even qualitatively on a graph that the net is purely like to hold the balloon inside, so it doesn't like slip out of the net or some like experimental limitations.
The quick, what would happen to efficiency in this case? Will it be higher or smaller?
Well, it would be the same.
It would be the same?
Mm-hmm.
Okay.
Like maybe as a further comment, since we have the same output energy as like from this graph, it is the same, and we also give it the exact like muscle energy. The energy inside muscle is also the same, so therefore, yeah.
Question to the reviewer. In your opinion, do you think the reporter has any missed important parameters?
I think the reporter did not have a sufficient investigation into the elasticity of the balloon because.
Okay, thank you. Does the opponent want to add something onto that?
Okay, the same answer as well as the lifting height
I think they should also change the lifting height and see how bringing the same mass to different height can affect the efficiency.
Yeah, I have one question left
Yeah.
for the reporter. So if you would use a balloon of a different shape, I mean,
Mhm.
except for the obvious
Yeah.
like geometrical change, is there anything else that would get affected by this in terms of efficiency?
Yeah, so the geometrical shape would significantly like affect the energy output. So yeah, it would affect probably the efficiency, and also like probably the way the rubber is stretched and to which what amount. So yeah, that would.
So
that
then
would
the
affect.
elasticity would have an.
Sorry.
So then the elasticity would have a significant effect. That's what you're saying.
Yeah, the elasticity has even effect like with
Okay, thank
our
you.
balloon.
Can you go to slide 50? And can you explain why for small volumes there is no numerical simulation points?
Yeah, it is like the volumes are very very small, so therefore like it is just a numerical feeling.
Another question, the distance on x-axis between the 2 points is just like 1 pump, 2
Yes.
pumps, 3 pumps, and
Yes.
so on?
Yes.
So they are the same?
Sorry?
Each distance on
Yes,
x-axis
each distance is the same.
To the reporter, did you change either the net or the balloon?
We changed the net parameters, however
No,
not
the actual net. You changed the parameter. Did you change the net?
like
use a
not
different
the
sort of
material
net.
or some other properties, but many relevant parameters of
So-
the net were changed.
No. And did you change the balloon?
No.
Okay. Do you have the balloon?
Sorry?
Do you have the balloon here?
Oh no.
Well, time. Thank you. Thank you. Big round of applause, I think. Okay, I believe that the judges, the jurors are now ready to release the scores. So I would like people to show the scores, please, for the presentation on the air muscle. And mine is a 7. And we have a 6, a 7, a 7, and a 7. Great jury panel. And going straight on to the discussion. The opposition. I gave it a 6, a 6, a 7, a 7, and an 8. And then finally, the review from Singapore of the thing. I gave it a 6. Oh, we have a 10. We have an 8, and a 7, and a 7. Well done, everybody. Okay. If you can give me the list. So, reporting the highest and lowest and justifying those. Dan, hang on. Yeah. So, this is the right fight? Yes. No. Hang on. Is this the right? Is it all on here? Is this first column?
No. It's middle.
Oh, it's the middle. Right. I thought it was reading one. Okay. So, lots of us gave 7s. How about we ask Grigoria to explain why you gave it a 7?
So, okay. Okay. First of all, good job with the report. You did a great job. For me, I liked your phenomenal explanation, and the theory model was good. You investigate some relevant parameters. I'm not really sure about the comparison between the theory and the experiment. You discuss it with the opponent at the end, and you give some explanation about the limitations and some of the, how can I say, errors or difference between the experiments and your theory. I would like to be maybe more active to the discussion with the opponent. I would like to see more dynamic from you, but you supported your opinion with your presentation, so overall it was a good report. So, thank you.
Okay, and we also had a 6 from Becca.
I don't think there is big range between 6 and 7, but still, I'm going to tell you, first of all, partial grades. It was 3 for the presentation and 2 for the discussion. I will say, first of all, I really liked you in the discussion. You answered all of the answers and tried to basically show your data as a proof, but I think the model was oversimplified. Too many assumptions. I know that you didn't fit anything and so on. I understand that, but most of the things were calculated kind of experimentally. The efficiency, those parameters are more of a, I don't know, experimental, rather than I wanted a lot more kind of theoretical explanation of how balloon was inflated, what kind of forces were there, maybe in terms of energies, also more theoretical ones. Yes, but overall it was a good solution. I don't think like between high and low points there is a big difference. That's why it was there.
Thank you. And then for the opposition, we had an 8.
I think this was a really nice opposition. I think you mentioned all of the important parts, and you really managed to challenge the reporter on the things that like were not clear and were also on my list. Like, for example, the plate elasticity, a bit of the setup and so on. So I think there was not much to complain about.
Well, I gave it a 6, and the partials were 1 for the questions asked. I thought there were a few things which I'd been keen to know about, which you didn't really ask, and you were going into a lot of detail about some of the questions I didn't think hit the mark. 2.6 for your speech. It's quite a nice speech. You used the time efficiently. You made lots of points, but I felt that there were certain points that you really missed. And then in the discussion, I felt there were, especially towards the end of the discussion, you were talking over one another. You did not prioritize the time effectively. I thought that the hysteresis and the inflating, deflating might have been quite a part of the discussion, but you just got shoved in on the end with you talking over him and not giving him time to answer and things like that. So I just gave you 1.3 for that, which ended up with the 6. And then for the review, we have a 10.
So first partial grades, I'm gonna tell you it was 2 for the questions. Questions were perfect, and literally you asked basically a lot of questions which I deleted myself because 3 of them I had prepared for the jurors' questions. Then 3 for the review of reports. I thought that you understood the review of report fully, and the pros and cons were presented perfectly. Basically, everything that you said that was con, I agree with it. Then review of opposition, I gave you 1 because I didn't feel like it was exactly like half good. Basically, out of 2, you got 1. And then review of discussion was 2. You literally presented every topic that was discussed, and all of the answers were answered. You presented your own opinions, and plus 0.5 because of the question of how it was inflated, because that's also important. I missed it from the presentation. And since you pointed out in fast questions and then answered it, during my jurors' questions, I think you understood it quite well, and it was the new topic introduced, so 9.5 got rounded to 10. Well done.
And I gave it a 6. So it just shows how we have different things we're looking at. So I felt that the questions were okay, but again, I felt there was important aspects of the. So my big thing with the problem, if I was looking for weaknesses, is I said, well, they didn't change the balloon and they didn't change the nut. But then you've gone on about the plastic bag thing, and I thought the plastic bag was great. I thought putting a plastic bag in there instead of a balloon shows what the balloon's doing, so that's really important. But obviously you didn't, and the reporter seemed to even think that you thought that you used the plastic bag throughout most of the experiments. I don't know if you did, but it kind of clouded things for me. So I wasn't sure if we were even talking about the same thing. I felt that there's probably, you've done the experiment and done certain things, and there was maybe a lack of flexibility to go another way and look at how things were being done. So I felt you were kind of putting that view onto what you did. So my scores were 1.5, 1.5, and 1. And it was 6 is a good score, but I wasn't knocked out by what you were. Didn't feel you brought any real meaningful insight into the problem. And I'm still writing, no one changed the balloon, no one changed the net material, no one looked into any of that. But you were still talking about it like it was a really important thing. So I felt that was the weakness. But otherwise, I really enjoyed it. I loved it. It was some great video, and it was a lot of fun. So well done, everybody. And we now have a 10-minute break.